Hello, I will briefly present you here two breakthroughs that you did for formally verified compilers in Coq. A formally verified compiler is a compiler with a proof of correctness. So all the transformations have to be proven correct. Our first breakthrough is to provide scalable scheduling optimizations. A scheduling optimization is one where the instructions are reordered. This kind of transformation is very hard to prove structurally. So we split it into an untrusted oracle which gives us a schedule proposition, and then we execute symbolically the return schedule to check its correctness. Our second contribution is that we are the first to target an interlocked VELIF processor, that is, a processor with explicit instruction parallelism. So here is a tiny example to introduce you the impact of scheduling. In this example, we assume that the add and sub have a latency of 1 and the load has a latency of 2. So we consider here a simple model, a 3-stage pipeline. There's the decode stage, the exec1 stage where add and sub finish, and exec2 where load finishes. In this example, if we run the instructions in order, there will be a stall because of the R3 register not being available. However, if we permute the instructions 2 and 1, we see that we win one cycle because there is no more stall. In practice, our untrusted oracle has a bunch of resource constraints and also latency constraints which depend on both the processor latencies and the original program. Then, to ensure that the scheduling is actually correct, we execute symbolically the original code and the scheduled code, and we check that they are the same. For architectures such as the Calliope processor, a bundle is a group of instructions that are to be executed in parallel. In our work, we define semantics for bundle execution. And then we use the scheduling path in order to generate bundles into COMSOL. So our verifier works in two steps. As mentioned earlier, the first step verifies the equivalence of the unordered and ordered basic block. And then the last step verifies that each bundle has the same execution between sequential and parallel semantics. Finally, we give some performance comparison. The top chart compares the performance of the original code to the scheduler. Compared to the original version without any scheduling, we gain 40% in average. And compared to a greedy bundler, we gain 20% in average. The bottom chart compares COMSOL to the GCC of Calray. Most safety critical applications use GCC without any optimization. We can see we always beat GCC 0.0 by a large margin. We also beat GCC 0.1 most of the time. As for 0.2 and 0.3, we are not there yet, but we are getting closer. In order to further bridge the gap, we are currently working on superburst scheduling before register allocation. I am going to demonstrate the COMSOL compiler and our optimization on a simple example. We are going here to see an example of a matrix multiplication. So this is the very simple code that performs the matrix multiplication. We are going to compile it, and we are then going to execute it and measure the amount of cycles. Now we will run COMSOL on the example without any post-pass optimization. So you will see the actual original code. So here is the code from the innermost loop, that one. This code isn't optimal at all because we only have one instruction per bundle. And also we have some stores in the pipeline. For example, we have this multiply add here which takes 2 cycles, except that we issue a load on the cycle right after. So that makes for very suboptimal performance. And if we try to run it, we get this amount of cycles. Now we will try to run COMSOL with the first version of the scheduler, which will just pack the instructions together into bundles. On this example, the oracle packed together some instructions and the verificator verified that this is actually correct. This will give better performance, however, we still have issues with stores, as you can see here. We can try to run it, and we see we're slightly better, but it could still be improved. So now let's try to reorder the instructions with our list scheduler. Here is the result. We can see that a lot of instructions have been moved, which results in a much more efficient code. In particular, we can execute 4 instructions at the same time on the first bundle. So now if we run that example, we can see we have a much better performance than before. Thanks for your attention.